Okay, in this video, I'm going to introduce three other types of IPS. In the last part of last video, I introduced the basic interacting process, right? That's a very fundamental basic um, type of IPS. So the first one I'm going to introduce in this video is called multiple contact processes. So there should be n types of particles interacting where n is equal to or larger than 2, and it should be an integer. So in basic contact process, we only have two states, 0 and 1. 0 represents vacant or vacancy. So there was only one particle, which is state 1, right? So here we should have two types of particles or even more particles, or we can say besides 0, we should have at least two other states or even more states, each with its own birth and death rate, which means each particle should have a specific delta value. Okay, and the competing contact model, no dependence between different types, right? The state of one particle has no effect on the other particle. They only compete for vacant space. For example, we have two particles, right? Particle 1 is addressed by state 1. Particle 2 is addressed by state 2. And of course, we have state 0 for vacancy. So particle 1 and 2, they both compete for vacancy, for 0. They both can occupy a vacant cell, but they cannot fight each other. Okay, that's the meaning for only competing for vacant place, for vacant space. They do not compete with each other. Okay, so surprising effects of computation. Okay, if the two types of particles, they have the same neighborhood. Of course, you can define different neighborhood for them because they only compete for vacant space, right? For example, Van Neumann neighborhood. Both types cannot coexist unless their death rates are identical. Delta 1 is equal to delta 2. So what's the meaning of delta? The higher the delta, the higher the probability that a living cell, will die after next tick. That's why it's called death rate, right? More generally, type with the highest birth to death rate ratio will win. Okay, beta is the proportion of its neighborhood that is alive, right? And beta decides the probability of what? Of giving birth for a specific particle. So the ratio between beta and delta is important. Okay, if there are two particles or even more particles, the one with the highest birth to death rate ratio will win. Okay, and here is the model you can play with in NetLogo. Okay, it's model 3.5. And here are some examples here. Snapshots of the two-state competing contact process. Two-state means 1 and 2. Of course, there is also a vacancy, which is 0. So figure A, both live states have the same death rate. Delta 1 equals delta 2 equals 0.5. So this is the only scenario that they will exist. They will coexist when delta 1 is equal to delta 2 is equal to 0.5. Okay, of course, you can change 0.5 to other values, but they have to be equal to each other. Distinct regions of state 1, white, state 2, black, against the vacant state, 0, which is gray. Okay, so A is a peaceful coexisting scenario for two particles. So in B, the death rate of white of 1 delta 1 is slightly higher than what? The death rate of 2. It's only a difference of 0.08. And you can say that black is totally dominant here. Okay, okay. And if you go on running this model, white will be what? Will be completely dominated by black, which means that the white cells will die out. Okay. For say it's the opposite situation of B. In say, although the death rates for both particles they are pretty low, but you can say that the death rate for white cells is a little bit lower than the death rate for black cells. This difference is even smaller compared to figure B. It's a difference of 0.02, and you can say that white cells, they are dominant here. They are dominant here. So this multiple contact IPS is very sensitive to the setting of death rate. And next, let's talk about IPS with direct contacts. So here, let's just say we have 3 states here, right? Grass for 0, bush is for let's just say 0 is for grass, 1 is for bush, 2 is for tree. Okay, it's still 2 states. Sorry, I said 3 states. It should be 2 states, 1 and 2, bush and tree. Let's just consider 0 or grass as non-state. Okay, so 0, 1, 2. Okay, and the bush and trees directly compete, which means that tree can beat bush. Not just they compete not only for vacant space. Okay, grass here is considered a vacant state because it's 0, right? Yeah, it's 0. You can say this is a 3-state scenario. It means that you consider 0 as a state, or you can say it's a 2-state scenario because grass is 0. It's not a part of computation. But here the difference with the difference between direct contacts and multiple contact is that here, these 2 states, 1 and 2, bush and tree, they compete with each other, and tree can beat bush. Bush cannot beat tree. Okay, so the model here, transition rules. Okay, grass is equal to 0, bush is equal to 1, tree is equal to 2, okay? Sites that are bushes or trees die reverting to grass at rates delta 1 and delta 2. Reverting to grass, it means 1 or 2 changes back to 0, okay? So still, we use delta 1 and delta 2 for their death rates. Sites that are bushes or trees gave birth by sending new particles to a randomly selected site in their neighborhood at rates beta 1 and beta 2. Okay, and if a new particle in state I arrives at a site where a particle with J is already present, then it replaces that particle only if I is larger than J. What does it mean? If I is equal to 2, J is equal to 0 or 1, then 2 will replace that 1 or that 0. It means that tree can invade bush and grass. Brush can invade grass. But brush cannot invade tree, of course. Grass cannot invade bush or tree. So tree replaces bush or grass. Bush replaces grass. Grass replaces nothing. Okay, okay. So here is another model. You can play with it. You can play with it in NetLogo. And here you should know that. What's the difference between IPS with direct contacts and and IPS with multiple contact processes. The difference is that whether the two particles or even more particles, whether they compete directly. If they are all competing for vacancy, then it's multiple contact process. Okay. If they compete with each other, like this one, tree can invade bush, then it's called direct contacts. Okay, so that's the difference. The third one, the third type here is even more complex. It's called cyclical relationships. Each state has one state that it can invade and one which can invade it. It's like the rock, scissors, paper game. Rock beats scissors. Scissors beat paper. And paper beats who? Beats rock. Okay? So IPS with cyclical relationships, it was proposed by these two scientists in 2001. At each time step, select a particle I at random, and also one of its neighbors J. If the states are the same, nothing happens. If the neighboring set dominates the central pixel, which means that the value of J is larger than the value of I, then the state of the central particle changes to that of the neighbor J, which means the central cell is invaded by that neighbor, randomly selected, right? Otherwise, the central particle dominates the neighbor, which means the central particle's value is larger than the value of the neighbor. And the neighbor site J switches to the central site I. So if we're talking about RSP, rock, scissors, paper relationship, you should be very familiar with that, right? Because when we were children, we played that, right, frequently. So there is this cycle here. Instead of grass, bush, and tree, there is no cycle. It's a food chain. But here is a food cycle. And here, theoretically, this is a model you can use in NetLogo to address cyclical relationships. And theoretically, equilibrium can be achieved at P1 is equal to P2 is equal to P3. And P here is the number of cells in each state. Okay, but this equilibrium is not static in a spatial model, which means that you can say here, you can play with it. So these three curves with different colors, they're representing the proportion of each type of particles within this space. You can see that this is a dynamic balance, dynamic equilibrium, which means that the proportions of them vary across time, but there is always this equilibrium. Okay, one cannot be too many. And results are different when you consider spatial context. So here in this video, I introduced the three other types of IPS. The first one, multiple contact processes, which means that there are more than one particles, right? But no matter how many there are, they always compete only for vacancy. And IPS with direct contacts, which means that these N particles, they do not only fight or compete for vacancies, they compete with each other. But this food chain is a food chain. This relationship is a linear relationship. There is no cycle. And if we want to make it even more complex, we have this cyclical relationship, which means that there is a food cycle, right? Type 1 beats type 2, type 2 beats type 3, type 3 again get back beats type 1. Of course, you can make this cycle even larger with 4, 5, 6 or n particles, but the relationship here is different from the former two types of IPS. Okay. Okay, thank you very much. This is a relatively shorter video, and yeah, thank you. See you in the next video.